Welcome, everyone. It is March 30th, 2002, and this is the ESIP soil cluster presentation by Luís de Sousa.
Very good, very good.
Excellent. Who is coming to us from the from ISRIC, the World Soil Information. I'm sorry, I don't know what ISRIC stands for, but Luís is a geoinformatician who specializes in thinking about how do we interoperate and present and talk about not only soil data, but broader geoinformatics in general. And today he's going to be talking about GlosSIS. And I'm really interested to get an update on this project. It's been really fun to follow the developments.
All right, so let's start by checking the technicalities here. So do we have all the presentation on our screens?
Yes, we have it.
Good. So let me start by saying that ISRIC stands for International Soil Reference and Information Center. And I guess GlosSIS is related both to the reference and to the information. Okay, so, well, first of all, greetings to all. Good afternoon, good morning, wherever you are. Good evening for me. Okay, so let's talk about the GloSIS web ontology. That's what I'm here for. The little outline of this presentation, I will start by leaving some notes on the Global Soil Partnership, where this all was born and raised, reference the international consultancy that started the technical work. I'll give a brief introduction to what is the Semantic Web, and then I will go into GlosSIS, first highlighting how the GlosSIS domain model was transformed to our ontology, provide a brief overview, also some notes on how to use the ontology and talk about future work. So usually, you provide the acknowledgements at the very end, but here I would like to start with the acknowledgements because GlosSIS is the outcome of years of work from dozens of individuals from many different institutions. And here I put the logos of, I think, the most relevant institutions that have contributed to GlosSIS. Probably missing some, if that is the case, I'm sorry. But just keep in mind, this is not just an institutional project, this is an international effort towards an information exchange mechanism. So let's talk about the GSP, the Global Soil Partnership. This is an initiative that is going on for a decade now under the auspices of the FAO. And it started as a network of stakeholders in the soil domain, with the goals of raising awareness to the importance of soils and help countries developing sustainable agricultural practices. And this initiative has managed to gather pretty much almost all the soil information institutes of the world that are gathered in the international network of soil information institutions, ISIP for short, that meets at least once a year. At least once a year they meet. The Global Soil Partnership was initially designed along 5 different pillars of action with topics such as soil management, awareness raising, research, information and data, and harmonization. And it's in pillars 4 and 5 where we start seeing references to quality of data, availability of data, and data harmonization. Around 2016, 2017, the GSP drafted plans of action for each of the pillars. And in pillar 5, there were a number of important difficulties identified that prevent the correct harmonization of soil data. The main problem is that soil data is collected usually at national or regional level. It's very focused on local context and pretty much unaware of the global needs and global use of that soil data. And this creates hurdles when you need to transfer or to share this data across regions, across countries. Usually it's quite a headache. And therefore, the GSP envisioned the development of a soil information exchange as a key priority within this Pillar 5 harmonization. Here I have a small excerpt from the plan of action of Pillar 5, defining what is the soil information exchange. And the essential words are, it's an information model providing a framework for our harmonization for the efficient exchange and collation of globally consistent data. So data exchange recognized as an essential component of harmonization, facilitates data integration, analysis, and interpretation. And I think above all, it's understood as a foundation not only of harmonization, but all of the Pillar 5s of the pillars of the Global Soil Partnership. Okay, so fast forward to 2019, I believe the GSP launched an international consultancy trying to gather a group of experts to look into this topic of the data exchange. And the work started still in 2019. The consultants started by creating an inventory of requirements, conducting meetings and interviews with the stakeholders in the GSP. And they, among many others, they identified two important requirements. First of all, is that this work under the GSP should recycle as much as possible existing assets. So basically, do not reinvent the wheel, just try to use whatever is out there to the best outcome. And secondly, the consultancy also needed to look into implementation possibilities. So by this time, 2019 had been already quite a good deal of work that I will reference ahead. But implementation, so how you get from these abstract domain models to actual things that work, there was still a problem that was not tackled correctly at the time. Correctly, or at least completely at the time. So the consultancy acknowledged that there is quite a good deal of work on soil ontology out there, and took into account 4 domain models and 2 data models. The model that was developed in Australia and New Zealand, the Inspire Soil Scheme, the model that is published with the ISO standard for soil data quality, which has this number 28258. These are all of the same vintage, interestingly. Also, the domain model that was used in the soil interchange experiment run by the OGC in 2016, and then the data models of databases where a lot of global soil data has been collated, GloSIS and earlier than that in SOTA. And one of the things that the consultants noted is that the 4 data models from Australia, Inspire, ISO, and OGC, they all share the same DNA because they all somehow relate to the observations and measurement standard that was issued in 2011 by the OGC and ISO. So the consultants then went on with their work, starting from the ISO domain model and augmented it with the properties and code lists that are published in the FAO guidelines for soil description. And here, this picture that you can't read, and that's fine, that's not a problem. This is just a section of the resulting data model. And what I want to show you here is that in gray, you have the original assets that were in the ISO domain model. And then in green and blue, all the new things that this consultancy created. So basically in green, soil properties, and in blue, the code lists that meet the soil properties. So this means a very, very relevant expansion of the domain model and towards a more practical use of this domain model. And finally, out of this consultancy also, this question of implementation. So how is this then put to practice? And the consultants identified 2 main avenues, one based on XML and pretty much following on the observations and measurements from a decade ago, and also opened the door to the semantic web. And primarily because of the sensor observation sample and actuator ontology that was published in 2019. And by the way, a few weeks ago, we had here a brilliant presentation on SOSA by Simon Cox that, if you haven't seen it, I would advise you to see it. It's quite worthy. Okay, so then into the semantic web, and if you allow me, hydrating my vocal cords a little bit. So this is a crash course in 3 slides on the semantic web. So what is the semantic web? It's an alternative or a different paradigm of encoding data, of recording data. And it works by observing the way that we talk about data in natural speech. So we talk about things, and if you remember your grammar from elementary school, you will recall that sentences usually have the structure of the subject, a predicate, and an object. So some examples here on a more ontological perspective. For instance, when I say that a house is the class, the house is the subject, is the predicate, and the class is the object. And so this is basically how data is represented in the semantic web, both in terms of ontological and the ontological aspect of it, but also data. So here is an example. For instance, the house in Koningsweg 101 has a roof made of thatch. So that's how data is recorded in the semantic web. So more practical things. In the semantic web, you have these triples composed by the subject, the predicate, and the object. And each of these elements, they can be of 2 basic types. First of all, it can be a universal resource identifier. So to make it simple, this is something similar to the URL of a web page that you insert in your browser. The URL in your browser is also a URI. What does it mean? It's an identifier that works wherever in the web. So we're no longer talking about identifiers and foreign primary keys in the database, but something that has to work everywhere in the world. And just a quick note, we can represent these URIs with abbreviations, but this will appear then in later slides, just to make it simple to read. And then beyond URIs, the triples can be composed of literals. And this is where the elements in the semantic web then are characterized. And then finally, an important aspect is that when we have a set of related triples, we end up with something called a knowledge graph. And there is this little picture here on the side, just to illustrate this. So you have to make a little bit of a mind shift here from thinking about data as tables and relations between tables to something that is more like a graph of elements that connect to each other. So, and to finish this brief introduction to the semantic web, some of the building blocks. Again, the URI, this is your coordinate system of the web. Most of the things that you see in triples are URIs, so they uniquely identify your resources wherever in the world. Then RDF. RDF is the basic syntax for data encoding as triples. And on top of RDF, there is the ontology, the web ontology language, which is abbreviated to OWL. This a funny exercise here, shifting the characters. And it's basically a language that allows the encoding of ontologies using RDF. And finally, the Sparkle query language, it's a similar idea to the SQL language that we use in the relational databases. Basically, it allows people to query an RDF resource and extract particular pieces of data from there. Okay, so I hope you have a better idea of what the semantic web is. Now, start to understand how then from the domain model that resulted from the consultancy, GlosSIS evolved to a web ontology. So this slide makes it all very simple. So essentially, there is a collection of guidelines that is gathered in one of the ISO standards for geographic information that provide the way on how to transform a UML domain model into an OWL RDF ontology. Now, this is all better said than done. So there is a lot of automation and a lot of nitty-gritty to make operation to do something like this, and especially in such an extensive data model. But luckily for GlosSIS, this came at a time where this project, SCU Soil, which is a partnership between the European Union and China about soil data and soil quality, where this topic was, or this question was on topic, and actually this work was possible within that project, and it was executed by Poznan University and resulted in a collection of RDF files that mirror the domain model as an ontology. Now, in doing this, there were two important ontological components, because this is again one of the main ideas of the semantic web, is that you use data and create data in the web, so in connection with the rest of the world, and you should use as much as possible existing assets and existing ontologies. And a key component of this, of the evolution of GlosSIS, is SOSA itself. And again, I recall that there is a previous presentation here at ESIP that is quite key to all this. But basically here we are talking of concepts such as observation, what is an observable property, the feature of interest, the procedure of that observation. And this was all taken into GlosSIS. And then a second ontology is the simple knowledge organization system, or SKOS for short, which is quite a simple ontology that is, I think it's almost everything included here in this picture. And it has the great advantage that it's very convenient to encode code lists. And this became also a key component of what GlosSIS came to be. And finally, the last step was the expansion of the ontology with the physio-chemical properties and the procedures to obtain values for those properties that were obtained from projects that have run in previous years at ISRIC, especially the Africa Soil Profiles project and also the World Soil Information Service. And the information that has been collated in those efforts was then transposed into GlosSIS with human-friendly descriptions, with bibliographic references, and always making use of URIs as much as possible. All right, so what is the result of all this? So first, let's start with the features of interest. The features of interest are what we are actually observing, and this structure is pretty much the same, exactly the same, that you find in the ISO 28258 domain model. So there is a spatial feature, spatial and special feature called plot. The soil plot is related to a surface, to a soil site. And then there is the profile that is cited usually on a plot. And the profile is itself composed by profile elements that can either be arbitrary layers or genetic horizons. So this is pretty much the pattern that you see in other soil ontologies, and it has taken ipsis verbis here to GlosSIS. And then we come to the observations, and this is where SOSA starts playing its role. So this is an example with a descriptive property. The descriptive property identifies the features of interest. In this case, the features of interest are the layer and the horizon. It identifies a property. In this case, it's the gypsum's forms, and then identifies a code list. And this code list is encoded with the help of SKOS. Now, for the physiochemical properties, the observations are somewhat similar. So again, the features of it are identified. A property is also identified, And then there is a result which is a numerical value, and this numerical value refers to a particular unit of measurement. And then what is different here from the descriptive properties is that these observations can declare a procedure. And the procedures, again, make use of SKOS, and they are structured as a code list. So speaking of code lists, this has, GlosSIS has grown to accommodate a very large number of code lists, especially for the descriptive properties. There are 40 code lists for the site and plot, 90 for the layer and the profile, 5 for the surface. And then there is a special code list for the physio-chemical properties and over 200 procedures. So this is the main, I would say the main addition to soil ontology vis-a-vis previous models with GlosSIS. It's these code lists. And well, this has grown quite a little bit. So it's quite a web of code lists and observations and SOSA classes, and they are all organized in different models. So there is a top layer with common assets, such as the code lists, a middle layer with the observations for the surface, site and the plot, the profile, the layer and the horizon. And then on a bottom layer, we have the features of interest that are primarily provided by the ISO 28258, the main model. Okay, so there is an ontology quite extensive out there, and what do you do with it? So allow me for a more iteration. So what do you do with the GlosSIS ontology? This is where things start to get really interesting, really funny from my perspective. So the ontology is available on the internet as RDF files composed of triples. And one thing I can do with those files, I can load them to something called a triple store. A triple store is a piece of software that is the equivalent to a database system in the relational world. So it stores triples and allows the user to query those triples. So if I load this bit of the ontology, in this case, we're talking of the code lists, to a triple store, I can do something that is pretty amazing, which is to query the ontology directly. And I don't want you to learn Sparkle in this presentation. What this bit of gibberish here means is something like, GlosSIS, please give me the codes and the labels that referred to the code list for landforms. And I ask this from the triple store, and I get something like this. So it's a list with the URIs for this code list, so a URI for a different code, and then the description for this code. And I can tell you how awesome it is to query an ontology like this. So this is very different from working with relational models or with UML. It's something quite special. Here is another example, and basically another Spark query that does something like, GlosSIS, please tell me what you know about the code list for landforms. And the result is a collection of predicates that are leveraged on SKOS and on the RDF schema that describe this code list. For instance, here that it's defined on table 5 of the guidelines of soil description, and it has a number of other labels that allows unequivocally to identify what all this is about. Okay, so that's using the ontology directly. But another thing that is really powerful with GlosSIS is the extension of code lists. And there's only one slide about this, but this is one of the real important aspects of GlosSIS. So imagine that I work in a country where the texture fractions are defined along these thresholds, 550 and 2000 micrometers. Currently, there is no procedure in GlosSIS to express something like that. And this example of texture fraction is actually quite common, so it looks like, or it feels like every other country defines texture fractions in a different way. So something like this will for sure happen in the future. Well, actually, with GlosSIS, it's relatively easy to simply extend the existing code list and add an additional procedure like this one. So here, this collection of triples, what is doing is defining a new element, a texture procedure with this particular thresholds, and declares it as, first of all, a concept in the SKOS ontology, but also as a texture procedure in the GlosSIS ontology. And then the other triples essentially provide the definition and the description of this procedure. So then if you have data to publish that uses this procedure for the identification of texture fractions, all you need to do is make this particular procedure available on the internet and then refer it from your data. The key idea that I want to convey with this slide is that GlosSIS is not a prescription. GlosSIS doesn't necessarily try to conform your data model, your data structures to a particular structure. GlosSIS is a framework, and is a framework that can be extended in different ways that allows you to provide the semantics for you to publish your data in a consistent way. Okay, so this is about the ontologies. So now let's talk about creating actual data, RDF data, GlosSIS compliant. And for this, I will give you an example with this awesome tool called Tarkle, which is a very simple but very powerful transformation tool that basically what it does is transform CSV files into RDF. So imagine that you have a very simple CSV file with a simple definition. It defines profiles, layers, and layer depths. So what I can do is to give this tool Tarkle another Sparkle query. And here, the important thing is this clause here, construct. Construct means give me triples, and these triples have the form of a URI, and then the identification of those URIs as being of the type GlosSIS layer. So I give all this to Tarkle, and Tarkle provides me triples, provides me an RDF file. And here in this example, what you can see are the URIs that identify the layers, and then the predicate and the object that identify that layer as a GlosSIS layer, meaning providing that kind of semantics. A slightly more complex example, another Sparkle query with the construct clause, basically give me the triples, and we see the same pattern as before, identify an element as a GlosSIS layer, and then identifying the profile to which the layer belongs and the depth interval of that layer. Again, I provide this to Sparkle, and I get a nice RDF file as a result. Again, the URI for the layer, identification of its type, and then the predicates and subjects that link it to the profile and provide then the literals with the depth interval. Okay, so this is all very, very, very cool from my perspective as a computer scientist, but I'm not necessarily expecting soil scientists to be doing this back and forth in the command line. If you do, great for you, but of course that's not really the realistic expectation. My main message with all this command line gibberish is that creating RDF from your existing data is not really rocket science. It's a relatively simple task. It might be laborious, but that's all that it is. And to do that, there are a number of tools available that help you transform your data into GlosSIS-compliant RDF. For the main programming languages, you have things like the RDF-lib library for Python, quite a sophisticated tool. For Java, there are also interesting options from the Apache Foundation, from the Eclipse Foundation, and even for a nascent language like Rust, there's already quite a sophisticated library called SOFIA. And you can even be more sophisticated than that. So if your data is stored in the relational database, there are actually off-the-shelf software that transforms relational data to RDF. These are two examples. Virtuoso and Oracle do that with a bit of a caveat, because this transformation from relational to RDF usually tends to be vendor specific. But again, just giving you an idea that there are many options and quite sophisticated to go from your current data to RDF GloSIS compliant. And I had here on the right-hand side this little picture, just to show what is the most important here is not this tooling and this automation, but actually to map from your current data sources into the ontology. And these are the yellow arrows here that show here how eventually you could do this, but this is the key aspect. This is where you are actually providing the semantics to your data. Okay, so now you have RDF files, and you want to provide that data. So that's the main target of GloSIS, the data providers. So an RDF file can simply be published to the web through an HTTP server. This is how RDF was envisioned 25 years ago when this all was being developed by the W3C. It's a very simple way of publishing RDF data. It's very cumbersome for the user, and it doesn't really scale. So you have a lot of data. This gets very nasty very fast. Another option is to use the software that I referred before, the triple store. So to use something, a program that stores triples and that provides them to the world through the SPARQL language, usually referred as the SPARQL endpoint. This is a powerful, very powerful option. It's application friendly, so it's easy to develop applications that use SPARQL then to fetch, query, to provide services, etc. But for the end user, yes, SPARQL is still, let's say, a bit of a threshold to go through, and especially for folks that are not so familiar with programming languages, this can be a hurdle. And then another aspect to consider is that if you expose a triple store like this, you can have someone creating a SPARQL query that is so complicated that it overwhelms your triple store. But there is a third way, and a third way that is emerging with the REST APIs that are being currently specified by the OGC, and they are pretty much a game changer in this domain. I would like here two aspects of the OGC APIs. First of all is that they refer to features and assets with URIs. And this in blue here, it's an example of a URI from the OGC API features that identifies collections and then items in the collections, and you could easily think that these items could be your soil plots, then with all the profiles and layers attached to it. Another important aspect of the OGC APIs is that they broaden the response formats available, and one of them is JSON. And well, great for us that RDF can actually be encoded with JSON. So this specification of these OGC APIs, it's pretty much coming towards the semantic web. And another aspect to highlight is that these new REST APIs, they go beyond the rigid hierarchies that existed with the previous OGC standards based on XML and WFS. We're expecting to have flat tables, the flat attribute tables, and some rigid hierarchies. And with these new APIs, you can start thinking of data as a network, or as we call it in the semantic web, as knowledge graphs. And so here on the right-hand side, a little image just to illustrate this, how this would work, or how does this work actually. So you store your triples, your GloSIS-compliant triples in a triple store, and then there is a piece of software that on the one hand is able to receive requests compliant with the OGC API specification, sends SPARQL queries to the triple store, and then replies to the user with JSON LD. And just a reference that this is fresh software, but it's pretty much functional software, and go at the moment developed pretty much at the initiative in Australia, where for some reason people seem to be always a few steps ahead than everybody else in this domain. So the future looks quite interesting in this regard on serving RDF within this context of GloSIS and spatial data. So yeah, so future, let's talk about that a little bit. So what comes next? One thing that is becoming a real priority is to set up a human-friendly code list. So we have this very large number of code lists and codes. They can be used with computer scientist tools, but they are not really human-friendly at the moment. So it is imperative to set up a code list index that allows users to navigate the code lists and get acquainted with them in an easier way. And this is just a little bit of an example of a software that does that. Another important thing are use cases. Last year, Poznan University ran a pilot with the Lucas dataset that had positive results. At ISRIC later in the year, I hope that we'll start tackling this with GlosSIS and start transforming GlosSIS data into GlosIS-compliant RDF. And an important aspect here is also to start producing user-oriented documentation, things such as a good practices or guidelines manual for data providers. What else? So this is also an effort that is important, is to facilitate the human engagement in the development and maintenance of the ontology. And again, we have this wonderful tool here that I'm such a fan, Tarko. And basically the idea is that we mirror the code lists, the RDF code lists as CSV files, making it easier for especially soil scientists to look into these code lists and expand and maintain and update them. And then with Tarko, this can be automatically transformed in RDF and be ready for use in the ontology. And the same way, if the computer scientists make changes to the RDF, there is a mechanism that mirrors that immediately in the CSV files, so that soil scientists can immediately understand what is going on with the ontology. This picture, or this little image, also shows something that an ontology is a living being and needs to be updated and maintained continuously. And there we get to another aspect of GlosSIS that is still yet to be set up, which is a governance, some kind of governance framework. And this is the way I see it eventually happening with a body that I call an ontology steering committee composed by computer scientists and soil scientists, and to whom the general public can submit requests for changes. Then the steering committee reasons upon the changes and eventually percolates those changes into the actual RDF. This is a framework that is very common in open source projects, and I think in something like GlosSIS can also be successful. Then looking a more long-term, the expansion of the ontology itself, one aspect that is still not included in GlosSIS, but it's ever more relevant in soil science and soil data, is soil spectroscopy. In that case, I don't think there are much hurdles there, because SOSA already includes a great deal of infrastructure towards that end, and I think it should, in principle, be sufficient to include a spectroscopy component in GlosSIS. And then another important aspect is soil cartography. There, things are not so easy. On the one hand, it's easy to describe the properties that the soil map displays with the current ontology, but there is no mechanism to describe how that map was derived, what kind of algorithms or statistical models were used to derive that map. And in that case, there are a few avenues to explore, primarily the machine learning schema that is being developed by the W3C. But there's also Stato, it's an ontology for statistical models, and also a data science ontology that is currently under development by IBM and Stanford University. So some challenges there to tackle in the coming years. So finally, come on and join us. These are the main gateways to GlosSIS. GlosSIS is currently developed and maintained in a repository at GitHub. So please join in, open issues. Yeah, have a look at the ontology. And there is also a community at Gitter where you can just ask questions and interact with the folks currently working on the ontology. If you have any doubts or any questions about how to use it and how to expand it. And that's about what I had for today. Thank you.
Thanks so
Thank you,
much.
Kate.
That was really exxiting. Yeah,
especially the command line bit, I guess. Yes.
So I'm going to open it up for clarifying questions. Hopefully we'll keep this to about 5 minutes, and then I'm going to stop the recording and we'll transition to an open discussion. So
should I stop the share? Share screen?
Go ahead and keep the share up.
All right. All right.
Anyone have any clarifying questions? Or maybe we'll just transition over to open discussion. All right, well, thank you so much, Luís, for such a really engaging and interesting update. With this, I'm going to end the recording.